So good afternoon to every students and happy Engineers Day to all of you. So now I hand over the mic to Suchishwita ma'am. Ma'am,
Thank you, Professor Chakravarti. So I can take the class right now. Is that okay?
okay. Okay, ma'am. Okay, ma'am.
Okay, thank you. Thank you. So happy Engineers Day to all the students and to all the faculty members and team of Chaivasa Engineering College. So with this engineering day, we can start with the new engineering subject of compiler design. So today only I came to know from Professor Chakravarti that all the attendees of this class are the 5th semester students, and being 5th semester students, I understand that the basics of compiler design is more important to understand instead of going too fast and covering the whole of the thing. So if whatever I have covered yesterday, if you think that anything is doubt or any difficulty that you find in understanding the concept from yesterday's class, I can still take a class today. Or if I was being a bit faster in a last class, you can let me know so that I can go a bit slower. Because understanding is more important than covering the things. So if you have any query, any of you, you just can unmute. You can ask me the question, or if you have any doubt, if there is any difficulty in understanding, maybe the language, if you want to tell me, explain me in Hindi, probably I will try, but I don't know whether I could be able to know. But I will try to explain that, or I can still try to explain in a very simpler way. So if you have any difficulty, students, you feel free to ask me, feel free to interact with me, and let me know your difficulties. Because what I believe is you should understand the compiler design. It's a very important subject, and this is related to your programming language, your data structure, your computer architecture, and rest of the things that you will be studying in subsequent semesters or even subsequent years also. So my sincere advice will be, if you have any query, if you want to ask me any question, never hesitate to do that. Please ask me the question, or you can always obstruct me, you can always stop me saying what you want to. If you want me to repeat the thing that I have explained, I can do that. So that's what will be my sincere advice. So any question from yesterday's class or anything you want to say, you can, you can tell me within this 5 minutes before I start the class. I like to hear from all of you. Any of you also, you can say me. Yeah, please let me know. See, if you don't say me anything, I'll understand that either you are not understanding or anything, or you are understanding everything. So any of this will be possible. So what you want me to assume you are understanding everything, probably, which is it's very difficult to believe, or you can ask me any question.
So all the students are requested, if anyone has any question, please ask to ma'am.
I think they hesitate to ask me the question, Professor Chakravarti. Might be.
Okay,
Or,
okay, ma'am.
so, but they should not hesitate actually. I don't know why they are not comfortable to ask me the question. But you can always ask. Even if you don't want to ask, you can send in the chat also. You can text in the chat. I can take the questions from there. So no worry about asking or no worry about anything. Just can text your queries in the chat. I can take them and I can answer your queries. So if not, then let me continue with the next lecture of compiler design. So this will be more of technical. So try to understand what I'm trying to cover or what I'll be explaining. Though the rest of the things, all the outline figured things may not be covered, but we'll first definitely cover the lexical analyzer and the parsing of the data. Probably both are new to you, so I'm not going to ask any question. But as we studied in yesterday's class, we understood that there is a lexical analyzer, there is a syntax analyzer, there is a semantic analyzer. And these three units are at the source code or at the front end of the intermediate language coder or intermediate language decoding, you can say. And there are two more units, if you remember, code optimization and code generation. Those two units are at the back end or towards closer to the machine system or machine language, right? So now out of the whole of the 5 units, we will take only 2 or 3 to analyze it properly to understand every unit in the more detailed way. So the first thing or the first unit that you might be remembering was the lexical analyzer, right? So in the lexical analyzer, the data that was generated that goes to the syntax analyzer or the semantic analyzer, right? So what happens here now? The source program that enters into the lexical analyzer, the first component of the compiler. What the lexical analyzer does, it creates the tokens. And if you remember, the token is nothing but a pair of entities that identifies a identifier and its symbol table entry, right? So that is why your lexical analyzer is connected to the symbol table. As we know, symbol table connects or symbol table has the entry for every unit or for every token. So these two are bidirectionally connected. Now the token that is being generated by the lexical analyzer enters into a unit called the parser. The parser is also called the syntax analyzer or more of a syntax analyzer, you can say. So we'll study what exactly is a parser. But before that, we will study how these tokens are generated, how the parsing is being done, and how the things are coming from the source code to the parsing tree. That's what is the objective of today's lecture. So we'll be confined within these 3 units in today's class. So if you'll see why we are separating the lexical analysis and the parsing. As I said, first is the your lexical analysis, then your syntactical analysis, then your semantical analysis. So before the syntax analysis, we understood that there is a lexical analysis yesterday. But today we are saying that lexical analysis is connected to a parser. So where this parser lies, is it a different entity from lexical analysis or it is a part of lexical analysis? Actually, if you say parsing is also a part of your lexical analysis, but we want to make them separate so that it will be easier or simpler to design, to understand, and it will improve the compiler efficiency. When the compiler will be designed, the efficiency of the compiler will be increased if we separate the lexical analysis and the parser. It also enhances the compiler portability. You know what is portability? Portability means the compiler can be taken from one unit to the other unit, meaning from one system to the other system. It is portable. It is lightweight. It can be carried from one to the other system. That is why we say this is portable. So now if we separate the parsing and the lexical analysis, two different entities, it becomes simpler and it becomes portable to transfer to any other unit. That is what is the merit or advantage of separating the lexical analysis and the parsing. So yesterday we studied about the tokens and the lexemes. So today we'll study more details about these tokens, patterns and the lexemes. What is a token? What is a pattern? What is a lexeme? Now a token is a pair of token name and an optional token value. If you remember yesterday, there was something called token was position, then it was integer or real. The type of the identifier was mentioned, right? So token is nothing but a pair of or an entry, a pair of two entities or two entries. One of them is the name of the token or name of the identifier, and another is the token value, which is an optional field. If you remember, there was a numerical 60. So when 60 was there was no value to that, meaning it is already defined as a token or as an entity which doesn't need any extra value or type. So the token has got only name thing. Then another is the pattern. Pattern is the description of the form that the lexemes of a token may take. This says what is the pattern of your lexeme. What is the pattern of your token? If we will take an example, it will be clear to understand. A lexeme, and in other words, the lexeme is a sequence of characters in the source program that matches the pattern for a token. So three things now you are seeing. One is the token that we studied yesterday, a pattern that we will study today, and a lexeme that we studied yesterday. But we didn't study that with respect to an example. So now we'll take an example to see what are these three things. See, first is the token, then is the pattern, then is the lexeme. And this pattern is nothing but your formal description as it is written. A pattern is a description of the form that the lexemes or token may take. So now, if there is a statement called if something, some expression, then a statement may occur or something like that. So one of the token is if. I say if is a token. Now how it is being described? The description or the pattern of if is, it is a set of characters consist of an I and a F. This is what is the pattern. And what is the lexeme says? The sample lexeme is if. Meaning this is a keyword or this is a token that has to be considered for a conditional statement or is considered as a program statement. Now there is another token called else. The pattern of else is, it is a set of characters with the character E, L, S and E. So if these four characters are written in this format, first E, then L, then S and E, it is considered as else. And this else is nothing but a token, and the sample lexeme is also token. Meaning what it says, the lexeme, a lexeme is a sequence of characters in the source program that matches the pattern for a token. So for this token, the lexeme is else. Right? This is what is being described in the description. Then the token says it is a comparison. It is a comparison. If the token says it is a comparison, then the description is what? What are the comparisons you can have? There can be logical comparisons, If you have done any programming, C programming or any programming, if you have done, you know that there is a comparison means there are some logical operations will be there. So what is the logical operation? One operation is less than. If you see, the first one is a less than, meaning when you compare two numbers, if x is less than y, meaning you are comparing two values, x and y. So that's a comparison. And how you write? The description is with a less than symbol or greater than. Greater than is also a kind of comparison. What you say? If x is greater than y, so the comparison or the expression is x greater than symbol y. This is a pattern. The token is comparison. Similarly, another token is or another pattern is less than equal to or greater than equal to or equal to or not equal to. So these are all the varieties of patterns. And these are the patterns, they are combined or they are being added together so that it goes for or it explains a token. And the sample lexeme for this is like this: less than equal to or not equal to, or it can be also greater than equal to. So this is what is the lexeme, and this lexeme is nothing but your comparison of two values. Right now you can understand the difference between the token, the pattern, and the lexeme. Similarly, I'll take another example here. ID. If you remember yesterday's class, there was in a token there are two things. One is the ID, the identifier, and the next one is a value to that ID. Right? So the token is an ID, but what is the pattern of writing that token? The pattern is first should be a letter or an alphabet, followed by letter and digit. Like I can say an ID is position. So position is one identifier. So that is identified as a token. Now the pattern is, the first one is P, an alphabet, and the rest of the things could be alphanumerical. Maybe alphabet, maybe numerical. I can say number one. This is also an ID, identifier. Number one, when I say, it starts with the alphabet N and followed by NUM, 3 characters and 1. So number 1. Similarly, I can say one num. Can I say this as a token, or can I say this as a pattern? One num. If you remember yesterday's class, it cannot be. The reason behind is the pattern says that the first character of an ID should be an alphabet. So if I said there is a variable or identifier one num, that means I am doing a mistake, right? So the pattern is letter followed by a letter or a digit. Now the sample lexemes are pi. This can be an identifier. This can be an ID because this starts with an alphabet P followed by another alphabet. Then score. This is also a valid one because it starts with an alphabet followed by also alphabet. So this is also a valid lexeme or valid token, you can say. D2. D2 is also possible because D2 starts with an alphabet and the next character is a number. So alphanumericals are acceptable. Now you can understand if I say a token, that means it explains something. It says about something. But the expression says or the description says how it has to be mentioned, and the sample lexeme says what is the exact token that you are using as the lexeme. Similarly, in another example we'll take, the token is a number, right? If I say the token is a number, the formal description says it can be any numeric constant. Any numeric meaning, it can be integer, it can be floating point, it can be exponential. So here you have the sample lexemes. 3.141, this is the value of a pi, right? So this is a sample lexeme, which is the token type is a number, and the information description is it's a numeric constant. Then it can be a 0 or it can be exponential, as I said, 6 into 6.02 e to the power 23. This is what is the sample lexicon. Then another thing is a literal. Let's say the token says it is a literal. And this literal is nothing but anything that will be within double quotation. If I say X, Y, Z, and I put that within double quotation, I say that is a literal. So one of the example is code dumped. Have you ever faced with this code dump error in your program while you are working in programming? If not, you might occur in future. Sometimes there will be something called code dump. This is a kind of error, or this is a kind of negative message for the user. And that is what is the code dump is a token, or that is a literal kind of token within double quotation, right? So here you can see there is a statement called printf total equal to %d / n score. So if I start with this, printf can be considered as a token, right? So this description will be it is the set of characters printf. This is the set of characters, fixed set of characters printf, and the sample exam is printf, nothing else. Then total. If total, the token will be an ID. Total is an identifier. So the description will be, it will start with an alphabet T followed by the alphabet or the numeric. And then equal to is a symbol, or you can say it is a comparison, you can say. Not exactly comparison, it is an assignment. So this is an assignment. Then your next one is your score. Score is a token which can be considered as an identifier. So your sample lexemes are your score, and the descriptions are that starts with S followed by any alphabet or any alphanumeric. This is what is the description about your token, your pattern, and your lexeme. So these three distinction you must be very clear to understand. Then only we can go for the further things and you can understand the more of this. Now we'll see what are the attributes of a token. So now you understand what is a token, right? So what is the attribute of a token? There is an equation called E is equal to mc square. This is a formula that you have studied in physics. E is equal to mc square. Now you see how it has been written. E equal to m star c double star 2. What it indicates, this equal to indicates there is an assignment symbol, meaning whatever will be calculated at the right side of the equal to will be assigned to the left side of the equal to. So this is what is the assignment symbol. So we will see what are the different attributes of the token. The first one, E, the first one E is an identifier, the token ID, right? So it says ID, it's an identifier. What it says, the next value, if you remember the token format is the name of the attribute, or name of the identifier and its corresponding location in the symbol table. So this is what it says, the token says this is an ID, and in the symbol table there is a pointer to the symbol table entry for E. So that value will be added here. If the symbol table entry is 0, this will be ID, 0. If the symbol table entry is 10, it will be mentioned as ID, 10. This is how the identifiers are identified in the token. Then comes the next symbol, the assignment symbol. As I said, this is an operand. Sorry, this is an operator. So what it says, it assigns the value of the right side to the left side. So this is an operator. Now this operator is mentioned as assign symbol. So the token name or token basic is, it is an assignment. And what is a kind of token? It is an operator token. So the kind of token is mentioned as assign, comma, or a hyphen operator. Then the next one is a variable or identifier M. So the token will be, this is an ID. ID means it is an identifier M. And there is a corresponding entry to the M in the symbol table. So whatever will be the entry value, that will be mentioned here. So here it says ID, comma, pointer to the symbol table entry. That is, if it is 4, as I discussed in the last class, if you remember, if the word size is 4 bytes, then if E starts at 0, M will start at 4, because after 4 byte only the next value can be stored. And if M is stored at 4, then M will consume 4 bytes. So the 4th byte, 5th byte, 6th byte, and 7th byte. These 4 bytes will be consumed by M. So the next identifier, when it will be stored, that will take the next value, that is 8. When you are considering every word is a 4 byte length. So depending on the word length, your sizes will be differing. So this is what is the entry in the symbol table. Now next one is the multiple operation. So multiple operation, the token says it is mult. Mult means it is a multiple kind of operator. So the value is, it's an operator. The ID is, or the first component of the token is, it's a multiplier and it is an operator. Then the next one is again an identifier, ID, pointer to symbol table entry for C. So pointer to this one is C. As I said, wherever in the symbol table the entry will be there, that value will be mentioned here. So multi is a ID, comma, the value in the symbol table. Then you have an exponential operator. Double star, you know, in C also you use this, right? So when you use the double star, meaning you are going to use the exponential operator. So that is what it says. This is nothing but your exponential and it is a kind of operator, right? And then the value 2. So this value says that 2 is nothing but a number and this number is an integer value 2. So just imagine when the equation simply written E is equal to mc square, it indicates that this is nothing but the different combination of different tokens, maybe an operator token, maybe an identifier token, maybe a number token. So all of this has got different 2 values or the pair of values in the token phrase or in the token, you can say pattern. These are called the attributes for the tokens. So then we have something, a new term that we'll study, but currently I'll just explain about what this is and we can study more details about this later. There is something called parsing. If you know about compiler design, there is something called parsing. This is also used, this term is also used in your programming languages. So what is parsing? Parsing is the process of determining if a string of tokens can be generated by a grammar. That means when your input program or source code enters into the compiler, there is something called a parsing unit which does the parsing job. And it says whether the string of tokens can be generated by the grammar. Grammar means, here I am saying about the context-free grammar. We'll see that later. So that grammar, what it will do, it will scan the statements and it will break it into number of tokens. So that is being done by a process called parsing. We'll see more about these parsings later. A parser must be capable of constructing the parse tree, or else the translation cannot be guaranteed correct. Who does the parsing? Who breaks the source code? Who generates the token? Is the parse tree. So, and the method is called parsing. So a parser must be capable of constructing the parse tree, and once this tree is generated or tree is built, your parsing is easily possible. And else the translation cannot be guaranteed. Without parsing, the translator or the compiler cannot have the proper outcome. The parsing recognizes sentences in a language. Every sentence has its own language. C sentence has got C language understanding. Java has got understood by Java language. So they are all language dependent. And the parsing recognizes the sentence in a particular language. Understanding that if you write something, it will say that this statement, whatever you have written, is for C language, is for Java, is for Python. So that is what is being recognized in the method of parsing. It discovered the structure of a document or a program. Every document or every program has got its own structure, and parsing identifies the structure of the document or the program. Then another is, finally, it constructs a parse tree, or it constructs a tree to represent the structure. What it represents? It represents explicitly or implicitly a tree, and that tree is called the parse tree. Meaning, in the lexical analysis, once the tokens are identified, the pattern is identified, the lexemes are identified, one can easily, or the compiler can easily make or easily build a parse tree. So more about this parse tree and all we will see. Just excuse me for 1 minute. Yeah. Now we'll see what is this parsing during the compilation, or how the compiler does the parsing. If you see the figure, you can see that this is a part of the figure that we saw yesterday. The source program enters into the lexical analyzer as we studied, as we saw in the last figure, and the output of the lexical analyzer goes to the parser. And then the outcome of the parser is nothing but a parse tree. So this parse tree enters into the rest of the front end. What are the rest of the front end? One is the syntax analysis, another is the semantic analysis. And after the semantic analysis, as we studied yesterday, the intermediate code will be generated, or intermediate representation occurs that may go to the rest of the unit for code optimization and code generation, all those things. So now we will focus around this lexical analysis and the parsing. So what happens, you can see here, in the lexical analyzer, there is another input called the regular expressions. What are the regular expressions? We will study subsequently. These are nothing but the existing expressions or existing things that are usually considered as required for the analysis or lexical analysis of the code. Now the outcome of the lexical analysis, as we studied, it generates the token, and that token goes to the parser. Also, one output of this lexical analysis go to the error handler, who handles the errors, who manages the errors. It goes to the error handler, or you can say error handling management or system. Then the outcome of the lexical analyzer is also connected to the symbol table, because the outcome of the lexical analysis is the tokens. And as we know, the token is always associated with a symbol table. It gives the location where the token is being stored. So you have a bidirectional link here, and then once the parser is activated, the parser means the change to the parsing tree. So this parse tree is the outcome of your parser, and also this parser sends its error report to the errors or the error module. So now this parse tree, whatever is being generated at the parser, it goes to the rest of the front end. And what happens in this? Collecting the token information, perform the type checking, intermediate code is being generated. This is what is being done in the rest of the front end, as we know, right? So this is what is called the intermediate representation. And to have all this in details, what it says, it uses a grammar to check the structure of the tokens. We know that the token are different types. It can be an identifier, it can be a numerator, it can be anything. It can be a comparison or any kind of thing. So it uses a specific kind of grammar to check what is the token structure. Then it produces a parse tree. A parse tree is being produced. Then the syntactic errors are reported and the recovery takes place. It recognizes the correct syntax. So in this table, what if the proper syntax has been maintained or not, that will be explained here. And finally, it reports the errors. So it also reports the errors. This is what is the details of the parsing during the compilation of a statement. So when you give a program code, you never think that so much of pre-processing or so much of faster processing is being actually done before you get your result on your test. So what goes behind is all these things that goes behind your computer when you put an instruction to it. So to understand the whole thing, let's begin with the parser, because this is a new term that we will study today. So let's begin with the parser. For simplicity, we consider the syntax directed translation of infix expression to a postfix form, a notation in which the operators appear after their operands. Probably I discussed in the last class yesterday. For any expression, there are three notations. One is the infix notation, one is the prefix notation, and another is the postfix notation. The way we write the equation A is equal to B plus C, this is a notation called the infix notation. The reason behind, the operator lies in between two operands. So that is why it is called the infix notation. The same notation can be changed or altered to either postfix or the prefix. Usually what happens, the computers do not understand the infix notation. So the computers, what it does, it converts the infix notation to prefix so that it can easily understand what the equation wants to do or how it is being computed. So This is what it says. For simplicity, we consider a syntax-directed translation of infix expression. And for example, the postfix of the expression 9 minus 5 plus 2 is 95 minus 2 plus. Do you agree or not? So what it does during the postfix, let me see. The expression written is 9 minus 5 plus 2 plus 2, right? So first the scanner or the lexical analysis starts scanning the first character, the first number, which is equal to 9. It is an operand. So what happens in postfix? All the operators go to the end of the operands. So there is an operation here 9 and 5, and the operation in between is minus. So if it is the minus is the operator, then this can be written as 9, 5 minus. That means first the operator comes, the operand comes, then comes your operator. So this is what is 9 minus 5 or 9, 5 minus. After that, what happens? Your next operator is plus and your operand is 2. So what happens? After the first 3 characters are being done, 9, 5 minus, it goes to the next operator 2. And after the operator, you have the operand. So what is the operand now remaining is plus. That means it scans from the left to the right and every operand is taken out and the operator is put at the beginning and then your operators are mentioned. So this is what is, the operators are mentioned and then the operand is mentioned. This is what is the postfix notation of any expression. So now you have the new postfix notation as 9, 5. No, this is not 95, right? This is 9 and 5 because 9 is a separate entity, 5 is a separate entity in the source code. So 9, 5 minus 2 plus. This is what is your postfix notation of your infix data. The simple translator handles expressions like 9 minus 5 plus 2, consisting of digits separated by plus and minus signs. This is what I told you now. It's a simple translator that will operate this operator and the operand separately, and the symbols will be also handled properly. One reason for starting with such simple expression is that the syntax analyzer can know directly with the individual characters for operators and operands. This is what is the syntax analyzer can do, or it can do work with very beginning directly with this individual characters for the operators separately and for the operands separately. We'll see how it does. So a lexical analyzer allows a translator to handle multi-character constructs like identifiers, which are written as sequence of characters. If you remember, so this is what we all studied all about is the parser or the parsing. The next one is your lexical analyzer. The lexical analyzer allows a translator to handle multi-character constructs like identifiers. So your position is an identifier, rate is an identifier, and in this program also you have used certain identifiers which consist of multiple characters, and they form an identifier which are written as sequence of characters but are treated as units called tokens during the syntax analysis. Though they are considered as the multi-character words or identifiers, but they are treated as the tokens during the syntax analysis. Next, we consider the intermediate code generation. So another part of the diagram is the intermediate code generation, which comes after the parsing tree or the parse tree. So what is that intermediate code generation? We'll see. One of internet code generation is called the abstract syntax trees or simply syntax trees. Represents the hierarchical syntactic structure of the source program. So this syntax tree, what happens? It presents the hierarchical syntactic structure of a source program. The way the source program is written, how it can be represented in a table or in a tree, you can say, that is what is the job of this syntax tree or the syntax analyzer. So we'll see this example. Before we see this example, just let's take 5 minutes break. Then again we'll be back. So don't switch off, don't log out. Just I'm just switching off. Audio and video off, and I'll be back in 5 minutes. So I also suggest all of you come back in 5 minutes.
Hello students, please wait for 5 minutes. After it will be started.
with the slides. What we have is the next, there is example. What we studied is a syntax tree, or what exactly is the tokens or the pattern or the lexemes are. How a syntax tree is created. Let us take a simple example of a do-while statement. You have a do-while statement. You have a do-while statement. It's written like this: do I is equal to I plus 1, while this one AI is less than B. This is a very simple programming statement, right? So now how the syntax tree is built from this statement we will see. So what it says, the whole of the statement is actually a do-while statement, right? So this do-while statement is mentioned and the root. And to the left of the do-while is the body. Body means what is the actual body of this code? You tell me. You have written multiple codes in C, right? So what is the body of this code? It says I is equal to I plus 1. This is what is the actual computing or the processing or the body of the do-while loop that has to be repeatedly done, that has to be repeatedly computed till a certain condition is satisfied. If you have written the do-while statement, you can understand that the do-while statement, this I is equal to I plus 1 will be repeatedly executed or repeatedly conducted till this condition is satisfied. So to work with this, what it does, the body is I is equal to I plus 1. Now in this I is equal to I plus 1, what are the things? One is I, there is an assignment statement, there is another identifier I, there is a plus operator, and there is a one number. So this is what is mentioned here, if you can see. I is equal to, assign is your equal to, right? I is equal to, if you go for the traversal, in order traversal of the tree, it says I is equal to I plus 1. It is always the left tree or the left branch, then the root, then the right branch. So if you start from the pre-order traversal in order traversal of the tree, it goes to the leftmost branch. So in the leftmost branch, you have the I. It goes to the root is equal to, then it goes to the rightmost. When it goes to the rightmost, there is another subtree. So it goes to the leftmost branch of the tree, which is equal to I, then the root, which is equal to plus, then the right child of the tree. If you have studied the data structure, you can easily understand what is the traversal. This is the in order traversal of the left subtree, and which is nothing but the body of your loop. So I is equal to I plus 1. It is the whole of the body. And this body will be repeated, or this processing will be repeated till or while AI is less than V. So this is what is been mentioned here. AI, so when I comes here, this becomes AI. Sorry, this should be less than symbol, is less than V. That means do this operation or body operation while your AI is less than V. This is one way of explaining your syntax tree. The other way will come to that. So in this, what it says, yeah. So what it says here, the root of the abstract syntax tree in the first figure, that is the tree-like figure, represents an entire do-while loop. A particular do-while loop has been mentioned there. It represents the do-while loop. The left child of the root represents the body of the loop, as I said, which consists of the only the assignment I is equal to I plus 1. This is what is explained already. And the right child of the root represent the condition, that is AI is less than B. So this is what is the syntax tree that is being obtained. Now, the other common interpreted representation is a sequence of 3 address instructions. If you go to the other figure, in the figure B, you'll see that there are 3 instructions are mentioned. What is that? I is equal to I plus 1. That means initially I is incremented by 1. Then temporary 1, in the temporary location AI is stored, and it is checked whether the temporary 1 is less than B, then again it will go to 1. That means step 1 will be repeatedly executed till your AI is less than B. And now your AI is represented as the temp 1. This is what is the another way of representing the statements. So you'll see that this form of intermediate code takes its name from the instruction of the form X is equal to Y operator Z, where operator is a binary operator. Why it is called a binary operator? You know what is a binary operator, right? An operator which takes 2 operands, 2 values to execute, that is called a binary operator. So in our case, X is equal to Y operator Z means it says I is equal to I plus 1. So it takes the value of I, it takes the value of 1, 2 values, and that are being operated with plus and gives a new value to Y. So here OP operator is a binary operator. Y and Z are the addresses of the operands. As I said, these are the 2 operands. And X is the address of the result of the operation. This is how the statement is being written. That means your syntax tree or syntax analysis either form a syntax tree or it will form a 3 address statement or 3 address instruction. A 3 address instruction carries out at most 1 operation, a computation, a comparison, or a branch. You will see here. This is a computation, this is a comparison, and this is one branch. Branch means go to 1 means the control will branch to 1. So there are at least 1 computation. Now we have 2 computations, I equal to I plus 1, and this is assignment 2 computations, 1 comparison, that is T1 is less than B, and there is another branching which is go to 1. This is what is your 3 address instruction that has been taken care of. So now I think we made it clear what exactly is a syntax tree does, what is how the parsing takes place during the compilation, and the different attributes of the tokens and all. Then we'll come to the another kind of concept called the context-free grammar, or we say this as syntax definition. So what is syntax definition? We'll see. This introduces a context-free grammar, or also called simple grammar, that is used to specify the syntax of a language. Now I say my name is XYZ. I will say name XYZ me. Do you understand anything? No, right? The reason behind this, I did not spell the sentence clearly or correctly. The sentence is mine, which is the subject or noun, name, which is the subject, is the verb, XYZ. So there is a format of writing the statement or English language, or there is a grammar to write this. The same is also true in any programming language. So what it does, every programming language has to follow a syntax in which it has to be written. So a grammar, or it's a context-free grammar, whatever you say, a grammar naturally describes the hierarchical structure of most programming language constructs. Every programming language has its own grammar. Like in C, when you write a statement, at the end of every statement, you put a semicolon. But when you write a Fortran program, you don't have to put a semicolon. Meaning, C has its own program, own grammar. Fortran has got its own grammar. C says that if you are writing, the C compiler will understand this is the end of a statement if you put a semicolon. But Fortran says you don't have to put any semicolon. If that is the end of the statement, that will be automatically understood by the compiler. So every compiler has its own grammar, and accordingly they understand the language or the program that has been written. For example, an if-else statement can have the form like this: if, expression, statement, else, another statement. This is how you write, right? So whenever an if statement is written, it is usually written if bracketed any expression. This expression is usually a logical expression. Logical expression meaning either a comparison will be there, logical comparison greater than equal to, no, less than equal to, not equal to, whatever may be, or there will be another logical operation, and or not. So any of the logical operation, arithmetic or logical operation, has to be done inside this bracket or inside this parenthesis. So what it says, an if-else statement is the concatenation of the keywords if and opening parenthesis. Parenthesis means the bracket. So how the different characters are being concatenated to express a particular statement, we will see. First, the keyword if, followed by an opening parenthesis, then an expression, then a closing parenthesis, then a statement, then the keyword else, then another statement. This is the whole grammar of writing an if-then-else statement in a programming language. If you miss any of them, then that will be treated as an error. And this is what is the defined syntax for the if-then-else statement. So there are certain languages you can use a keyword then, or you may not use the keyword then. This is automatically understood. But minimum this much has to be written to express an if-then-else statement. Now, using the variable expr, instead of writing the whole expression like it's spelling wise, we can use a character or an identifier or a variable, you can say expr, to denote the expression. And the variable statement can be replaced with a stmt. This also denotes the statement. So the structuring rule can be expressed as statement can have the form. That means if then else statement is a statement. So this statement can have the form if, expression, statement, else statement. This is what is actually was written there. Now I added a new thing. The statement can be written as, or the if then else statement can have the form like this. So in which the arrow may be read as can have the form. So your statement can have the form. Your statement can have the form of if, expression, statement, else statement. Such a rule is called a product sum. So this is what is a rule. This is what is a way of writing. A statement can have the form if, expression, statement, else statement. The whole thing is called a product sum. Now you understand? These are the key words you have to remember. You have to understand while understanding the compiler design. because other than these keywords, we cannot proceed further. So these are the things you must remember. So in a production, the lexical elements like the keyword if and the parenthesis are called the terminals. So any keyword that occurs at the terminals, these are the lexical elements. If is a keyword that is a terminal. A parenthesis, the closing parenthesis, the opening parenthesis, that is a keyword. That is also called as terminal. Else can also be called as a terminal. So whatever keyword existing in this, they are called the terminals. And the variables like expression, the statement, represent sequences of terminals and are called non-terminals. So any variable you are using, any expression you are using, any statement you are using, they are non-terminals. Whereas the keywords, the tokens, they are all the terminals. And the way of writing the whole thing is called the production. So these are the key statements or key things you have to remember for compiler design. So in the context-free grammar, or what you say in the simple grammar, you can say instead of context-free grammar, I can say this is a simple grammar. This has got 4 components. Very important thing you have to remember this. One is the set of terminals or set of symbols, sometimes also referred to as set of tokens. The terminals are elementary symbols of the language defined by the grammar. They are the elementary symbols, you can say, or like if keywords, if, else, then the parentheses, these are all the terminals. There are also a set of non-terminals, sometimes called the syntactic variables. Why it is variable? Because it can change. You can give any name for that. So they are called the non-terminals. Each non-terminal represents a set of strings of terminals. Right? So now you can highlight this. Each non-terminal represents a set of strings of terminals. That means whenever I say a statement or a expression, they also represent a series of strings of terminals in it. Then another is a set of productions. What are the productions as we discussed? Where each production consists of a non-terminal called the head or the left side of the production. What was the non-terminal here? The statement, right? That was the head or the left side of the production. An arrow and a sequence of terminals or non-terminals or and non-terminals called the body or right side of the production. So if you go to this, if this is the whole thing is a production statement, if this is a production, then this is called the left side of the production and this is called the body of the production or the right side of the production. And the left side of the production and the right side of the production are separated by an arrow. So one is the head, another is the body. One is the left side is the head, right side is the body of the production. And there is another term, a designation of one of the non-terminals as the start symbol. There is something called a start symbol, which is also called a designation of the non-terminal. Non-terminal means whatever is the being used by the user, not a keyword, right? That is called also a designation or a start of the symbol. Yes. Now, to go more details about this, we'll now understand this. We specify the grammars by listing their productions. Whenever we specify a particular grammar, we have to first list what are the productions. Means every production with a head and a body, what are the different productions available in it? With the productions for the start symbol listed first. And every production will start with the we'll begin with the start symbol at the beginning or listed first. We assume that digits, signs such as less than, equal to, and bold-faced strings such as while are the terminals. We have already seen that, right? All the keywords are the terminals. An italicized name is a non-terminal, like expression as we studied here. What are the italicized terms here? Statement, expression, statement, again statement. They are all made in italic. So if they are in italicized, then they are the non-terminals. And any non-italicized name or a symbol may be assumed to be a terminal. So if it is a terminal, it is written in the normal font. If it is a non-terminal, it is written in the italic form. For notational convenience, productions with the same non-terminal as the head can have their bodies grouped with the alternative bodies separated by a symbol separator, a bar, which we read as or, right? So if there is a separator between the alternate bodies, or we have two bodies, like two bodies means the right side of the production, right? For a single head or single left side of the production, if you want to have two alternate bodies, then you can mention both the bodies by putting a bar in between. This bar indicates the or. So before going for the next thing, we should have a clear-cut idea about what is a token and what is a terminal here. So what we understand terminal is the keywords, right? Those are the keywords are the terminals. They are also called the tokens, but the non-terminals can also be the tokens. So what is the difference between a token and a terminal? Like if I say X is equal to, or the statement is equal to if expression, statement, else statement. So expression is a variable. Expression can be anything. So that can be a terminal. That can be also a token. So how we say that how a token is different from a terminal? In a compiler, the lexical analyzer reads the characters of the source program. As I said, scanner. Lexical analyzer is nothing but a scanner. So it scans every character of the source program, groups them into lexically meaningful units called the lexemes. As I said, comparison. Comparison means it should be less than, equal to, not equal to. So every character, when it combines or it groups them, it finds a meaningful outcome, a meaningful unit. They are called the lexemes, and produces as output tokens representing these lexemes. So once the meaningful output has come, it says that this is a token and produces as output tokens representing these lexemes. So a token consists of two components we studied yesterday. One is the token name and another is the attribute value. What is the attribute of the token? The token names are abstract symbols that are used by the parser for syntax analysis. The token name can be anything. It can be an identifier, it can be a comparison, it can be operator. So these are all these symbols or these names are the abstract symbols, you can say, that are used by the parser for syntax analysis. Often we shall call these token names as the terminals that we studied. The tokens that are being used or that are having the abstract symbols in the syntax analysis are called the terminals, since they appear as terminal symbols in the grammar for a programming language. The attribute value, if present, is a pointer to the symbol table. That also we understand. Because if I say X is equal to something, X is a terminal, or what you say X is a token, and the other value associated with the token is the value in the or the pointer to the symbol table. And the pointer in the symbol table contains the additional information about the token. What are the additional informations? Yesterday we studied. The additional informations can be type, whether it is a floating point or integer, then when it is being generated, when it is being updated. So all these values will be stored in the symbol table. This additional information is not part of the grammar. So in our discussion of syntax analysis, we only refer to the tokens and the terminal symbols synonymously. So either we say about the token or we talk about the terminals in our subsequent studies. Let us take an example here. Consider a string. Let us take, we have a string 9 minus 5 plus 2. So what are the components in this? It contains two operators. One is the minus operator, another is the plus operator. And it has got three operands. What is the operands? One is 9, another is 5, another is 2. Three operands and two operators. So how the lexical analyzer scans it and considers it. Since a plus or minus sign must appear between two digits, we refer to such expression as lists of digits separated by plus or minus sign. Usually it is treated or it is called as two digits separated by a symbol. And what is the symbol or sign? Either a plus or a minus sign. So the syntax of the expression can be expressed as a production. What is a production we said? Production has a list, production has a head in the left side, it has a body in the right side. So what is the production? The production is, it is a list that can be expressed as list plus digit. Or it can say the list can have the list minus the digit. So, and finally the list will be the digit. Meaning, first you see, first list will be list plus digit. What is the list plus digit here? I can say 5 plus 2. That will be 7, right? So that will be the new list now. So now the new list is 5 plus 7, 5 plus 2, that is 7. Now the next list is list minus the digit. What is the digit now? 7. So list minus digit is now 9 minus 7 is 2. Now this is what is the new list that can have the form as a digit. So now the now list, what is the outcome of this? The body of the expression is only a digit. And this digit can be anything. It can be 0, it can be 1, up to it can be 9. With a separator or with a bar or with a OR symbol. This is how is the production look like or production is written. That means you have two operands, two operators. So you have two operators used. One is the plus operator, another is the minus operator. And this is how it then that there is an assumption or the assignment. This is what is written as the list can have the form of a digit. This is how is the a string of mathematical equation is represented as. Now, the bodies of the three productions with non-terminal list as a head equivalently can be grouped. You see the three productions. What are the three productions we have? We have one production here, list. Can we have the list plus digit? List can have the list minus digit, and list can have the digit. These are the three productions, right? So what it says, the bodies of the three productions, body means the right side of the three productions, with non-terminal list as head equivalently can be grouped. Meaning, the non-terminals, what are the non-terminals here? The list is the non-terminal. and that non-terminal is used as a head. Sorry. This list is a non-terminal, right? This can be a terminal because this is a keyword or a number valid. So, but this is a non-terminal. So this has been used as a head here. Here also this non-terminal is used as a head, and here this is also a non-terminal with a digit that is also used as a head here. So what it says, the bodies of the three productions with non-terminal list as head equivalently can be grouped as list can have the form like list plus digit or list minus digit or simply a digit. Now you see the whole thing is being now reduced to this form. Your 9 minus 5 plus 2 is now written in this form. List as the head and the body as list plus digit, list minus digit, and the digit. So according to our convention, the terminals of the grammar are the symbols. What are the terminals now? The terminals are plus, which cannot be changed, a keyword, the minus, then 0, 1, 2, 3 up to 9. These are the different digits that can be used. So these are the terminals of the grammar, and non-terminals, as we saw, these are the list and digit are the non-terminals, and the production is like this, right? So the non-terminals are the italicized names as the list and the digit, as I said, and terminals, these are the terminals non-italicized, with list being the start symbol because its productions are given first. So list is also as the start symbol or the head of the production, and the other is the body of the production, and list is used as the start symbol because its productions are given first. So these are the productions whose header, if you remember the first one, what is the start symbol? In this, it says the start symbol, a designation of one of the non-terminals as the start symbol. So because list and digits are the non-terminals, so we use list as one of the non-terminal that can be used as a start symbol, right? So I think now I could make it clear up to this, how the scanning of a signal, a small statement in the code is written, how that is being scanned, how that is being categorized as terminal, non-terminal, production, and a start symbol. If these things are clear, we can proceed further to see how a parse tree is being done. So we say a production is for a non-terminal if the non-terminal is the head of the production. That means in our case, our non-terminal was, what was the non-terminal? Your list. So we can say the production is for a non-terminal because our head is the non-terminal list. A string of terminals is a sequence of 0 or more terminals. Similarly, terminals can be a sequence of 0 or more terminals, and the string of 0 terminals written as an epsilon is called the empty string. Meaning epsilon is an empty string, meaning if there is a terminal where there is no string, or there is a string where there is no terminal, then either there can be one terminal, or there can be 0 terminal, or there can be more terminal. That's what is a string. So with a 0 terminal string, we mention that as an epsilon, meaning it doesn't have any string associated with it. So there is one term called the derivations. What the derivation says, a grammar derives the strings by beginning with the start symbol. A grammar derives the strings by beginning with a start symbol and repeatedly replacing a non-terminal by the body of a production for that non-terminal. This is what is the derivation. We'll see that with an example later. That will be more clear. And the terminal strings that can be derived from the start symbol from the language defined by the grammar. This is what is the derivation, but I'll explain this derivation with a suitable example. Probably today it is not there, but I'll explain what this derivation is with a suitable example maybe in the next class. So with this, now we can think of what is a parse tree. So a parse tree is pictorially shows how the start symbol of a grammar derives a string in the language. Meaning what it says, the start symbol. As we said, what is a start symbol? The start symbol can be a non-terminal that has to be kept in the left side or head of the production. So a parse tree periodically shows how the start symbol of a grammar derives a string in the language. So if non-terminal A has a production like this, if A is a non-terminal and this has the production like A can have the expression like A, X, Y, Z, then a parse tree may have an interior node labeled A. This is what is an interior node, right? So we'll talk about what is an interior node. If you say the tree, if you know the tree about this, tree has always a root node, and it has a left child, it has a right child. And if it has no left child or no right child, meaning it doesn't go in that direction. So we say that is a null branch or null child. And two nodes at the same level of a tree are called the siblings. You know this from data structure, right? So, and what is an interior node? An interior node is a node which has got both the left child, the right child, or maybe any other sibling child. So in this case, you'll see that if we have a production like this, A with an arrow of X, Y, Z, or what we say A can have the form of X, Y, Z, then the parse tree may have an interior node labeled with A, with 3 children labeled X, Y, Z from left to right. So now A is the interior node, and A has got 3 children, X, Y, and Z, and this is what is mentioned in the production. A can have the form of X, Y, Z. This is what is the parse tree. Then we can have the detail about this parse tree. As I said, who creates this parse tree is the parser, right? So the parser, the output of the parser is the parse tree. Now we'll see how the parser generates the parse tree. Formally, given a context-free grammar, a parse tree according to the grammar is a tree with the following properties. So what is a parse tree? First we understand. If we understand what is a parse tree, we can understand how the parse tree is created by the grammar. So for a context-free grammar, what is a parse tree is, it has the following properties. First, the root is labeled by the start symbol. So now you remember what is a start symbol? Start symbol is the head of the production. That is considered as the start symbol, usually. Not mandatory, but usually. So it has to start with the start symbol. It has to be labeled with the start symbol, that is the root. Each leaf is labeled by a terminal. If it has a terminal, terminal means the keywords. So every leaf node means the child node. The child node is called the leaf node, who doesn't have any other child. In a tree, the leaf node is the node which doesn't have any other child. If it has a child, we don't say that is a leaf node, right? So go deep into the tree, starting from the root. And if there is a leaf node, every leaf node will be labeled with a terminal by, or if there is no terminal, then it will be represented by an epsilon, saying that there is no terminal available for this leaf node. Each interior node is labeled by a non-terminal. So your root has the start symbol, leaf has the terminal symbol. So in between the roof and the terminal, whatever is the intermediate nodes or intermediate labels, at every intermediate terminal or at every, you can say the interior node will be labeled with a non-terminal. And what is the non-terminal? We now understand. Non-terminal is nothing but the identifiers or the expressions or the statements. Those are not keywords, right? So now this is what is up to root, leaf and interior. So if A is the non-terminal labeling some interior node, let us say A is any in between non-terminal node of a tree, then and xi to xn are the labels of the children of that node from left to right, then there must be a production A symbolized, or A can have the form of x1, x2, xn, where xi being a terminal or a non-terminal. Meaning for every interior node having the children can be represented as a production with the head as the non-terminal symbol and the body as the children. For a special case, if A has the production as epsilon and that is a production, then a node labeled A may have a single child labeled epsilon. That means if for any special case, if A becomes A doesn't have any child, or it has no child, or a child having a label of epsilon, meaning no terminal is there. In that case, the production can be A can have the form of epsilon. This is also possible in case of a parse tree. I think now you understand how the parse tree is built. So before we go for the more details about the parse tree, there are basically different types of parsers. Who creates the parse tree is the parser. Or you can say the part of the lexical analyzer who actually creates or builds the parse tree. So there are different types of parsers. One is the top-down parser, another is the bottom-up parser. In the top-down parser, again there are two types. One is backtracking parser, another is predictive parser. In the bottom-up parser, one is the left-right parser, or what we say LR parser, and another is the shift-reduce parser. And LR parser is again SLR, LR and LALR. So these are the different kinds of parsers. If time permit, we'll go for all the details of the parsers. But most important we understand is a top-down parser and a bottom-up parser. This is what is the classification of a parser. So we say there are basically two types of parsers, top-down and a bottom-up. What happens in the top-down? It starts at the root of the derivation tree and fills in. Starts with the root and subsequently it goes on filling the different interior nodes, the children node from the top to bottom. It picks a production and tries to match the input. What does it mean? Picks a production meaning it takes any interior node and its children as their body. So that becomes a production now. And once it picks the production, it tries to match with the input, if that is actually the input given or not. It may require backtracking. We'll see what exactly backtracking is when we study more about the top-down parser. And some grammars are backtrack free, or also called the predictive parsers. Then coming to the bottom of parser, which starts from the bottom or the leaf node till the root. It starts at the leaves and fills in. As I said, node, the bottom nodes are first started and then slowly it goes on filling till the root node comes. It starts in a state valid for legal first tokens, and it uses a stack to store both state and sentential forms. This is a little bit tricky. We'll study about this when we go for the bottom up, but the most easiest one is the top down parser. Once you will be thorough about the top down parser, you can easily understand what is a bottom up parser is. So we'll study about this top down parsing. What exactly is top down parsing? So the top down parser starts with the root of the parse tree. As I said, it starts from the very beginning or the root of the parse tree, labeled with the start or goal symbol of the grammar. So by now we understand what is a start symbol, right? What is a production, and out of the production, how a start symbol is derived. So that start symbol becomes the root of your parse tree. Now to build a parse, it repeats the following steps until the fringe of the parse tree matches the input string. So how the parse tree is built? Step 1. At a node labeled A, select a production. A can have the form alpha and construct the appropriate child for the symbol alpha. If alpha is B, C, then A will have two children, B left, C right. If alpha is XYZ, A will have three children, A left, X left, Y middle, Z right. So accordingly, for the production of A can have the form of alpha, depending on the symbols of alpha, we can have the appropriate production. Then when a terminal is added to the fringe that does not match the input string, backtrack. If we find that there has been a terminal that we have added to the interior node, but that actually doesn't match with the input string, then we have to go back and do it repeatedly. Then find the next node to be expanded. Then the next node is sourced and the next node is expanded in the form of the production. And the key is selecting the right production in step 1. What it says, the key is selecting the right production in step 1. So what it says in the step 1, what will be the right production? That actually decides your parse tree. So once the production decided or selecting the production selected is correct, you can have a correct parse tree. This is what is the steps for your top-down parsing. Now we'll see a top-down parsing, a simple top-down parsing we'll see. See, example of a top-down parsing. Now, suppose the given production rules are as follows. S is the head, or you can say the start symbol, has the form of AAD or AB. You can have any of these two, right? As I said, different terminals can have the different OR symbols. So with this, what it does, the start symbol is first started here, right? So first is the start symbol S. Then the operand or the production is decided as AAD. So you can see that the start symbol S is having three children. One is small a, then capital A, then D. This is what is the actual first production from the first statement, you can say. Then the second statement says that your capital A has another production to either a B or a C. Now we can have for this capital production sorry, for this capital A production, we can have B as the child, right? So generated is AB, input is AC or BD. So this is what is the parse tree is generated. Other way of generating this is we can go backtrack, and if we go backtrack, you will see that A can have another body as C. So now you can have A another body as C. So if this one is there, then we can go for the other symbol or other production S, which is can have represented as small a and capital B. So this is what is S having the small a and capital B as the as the as the two children. And now there is another thing for called the for this capital B, there is a production of CCD. So for this capital B, it says there are three productions or three body parts C, C and D. So these are the different possible top-down parsings that has been done for these productions, three productions, S, A and B. But now how we'll see that which one is correct, whether backtracking is required or not, that we can explain once we'll go more about this top-down parsing. So what we can do is so up to this now I think we understand what is the top down, what is parsing, how the parser is being designed, how the terminals, the non-terminals, the production, the start symbols, they are identified, and to represent a production, how a parse tree is constructed, depending starting with the start symbol and keeping all this what you say the body part as the children of the start symbol or the head, you can say. This is all about the parsing. Now I can take a quick question. If you have any query, you can ask me now. I think up to this it is clear to understand the parsing and the rest of the things that we studied. I can just have a quick review of what we studied today. So now you understand lexical analyzer. This lexical analyzer identifies the terminals, the non-terminals, the production, everything, and it enters into the parser, and the parser gives us the as a parse tree. So up to this we have studied, but again, this is not all about what we studied. There may be some error, there may be some backtracking required, so that again the parsing has to be redone, and we can have the new parse tree if the production does not match the input. That is what we studied, right? So up to this, any query? Please ask me if you have any query. Otherwise, Subham sir, are you there?
Everyone are requested to ask ma'am if anything you want to ask ma'am.
Yes, sir. What I was suggesting is, so can we stop the class today so that I can take some extra hours tomorrow? Because actually I have a meeting at 5 o'clock today. So can we stop today for today's session? I can take some extra hours tomorrow because tomorrow I'll be free.
Okay ma'am, there is no problem, and thank for such a wonderful session with us. So thank you ma'am, thank you for everyone to attend the session, and we will again start our meeting from tomorrow at 2:30 p.m. sharply. So thank you, ma'am. Thank you, everyone.
Yeah, thank you. Thank you all.
Okay, okay, ma'am.
Thank you, ma'am.